Okay, so let's get started. Welcome back to the Topos Institute Colloquium. Today we have Andrea Censi talking about categorification of negative information using enrichment. I just wanted to mention a brief story. I met Andrea when he was at MIT and invited me to give a talk in Lids. I gave a talk there. Afterwards, we talked for like maybe 30 minutes or something. And then 6 months later, Andrea had come back with a trace monoidal category of co-design, which became probably my favorite chapter in 7 sketches. So I really appreciate his stuff, and I hope everyone here does too. So go ahead, Andrea, whenever you're ready.
Thank you, David, for the introduction. I think I remember a different story, and I remember basically David opening up this work to me, which has really expanded my mind. I should say I'm not a mathematician. Actually, I'm a roboticist. I got a PhD in control dynamical systems, but I always had like an interest in the more theoretical part, and yeah, I'm fortunate that I can get to do some research in, I don't know if this is category theory. I guess it is, yeah. So this is, I already gave a short version of this talk at the ICT conference 1 month ago. So this is an extended version of the talk. But there's also something different in the math, because this is very much a work in progress, and it gets better by the week. So this is a joint work with Dr. Jonathan Lauren and my PhD student Joel Zardini. I will talk about negative information, and I will motivate it from practical application, robot motion planning, and this is something that really shows up all the time in our applications, and the question is, how can we treat it categorically, right? And we propose a formalization in which, in parallel to morphism, which represent in our mind positive information, we also have negative arrows that we call norphisms, so norphism. We define a nategory as a category that has also this norphism and the accounting necessary. We will see how these norphisms compose. They don't compose like morphism. So two morphisms that are compatible can give another morphism. However, a norphism gives another norphism only with a catalyst morphisms. So this is very interesting, and so the first part will be mostly about this new structure, this new algebra. The second part is about zipping this information using a rich category theory. So this is the, let's say, statement of our result. As you might remember, if you define P to be a set with the Cartesian product as a monadal product, a P-rich category provides the data for a small category. I will show you that a PIAN rich category provides the data for a nategory. And this is the new part. So last week at the conference, we had our own PIAN created from scratch. But now we managed to make it as an extension of Valeria de Paiva's GC construction. All right, so here's my example, robot motion planning. Robot motion planning, we have to find the optimal path between two robot configurations. And the path should typically avoid obstacles and minimize the cost. The cost could be time, could be fuel, could be energy. This you can really define as a category where the objects are the points in free space and the morphisms are the paths. But not only the paths, they also have an associated cost. Morphic composition concatenates the paths and sums the cost. And now you can also do any other associative operation here. Now, the basic path planning algorithm we teach is Dexter's algorithm. So this is the formalization where you actually have a discrete space, where these points are the discrete configuration set. You have a start point, you have a goal point, and Dexter's algorithm, what it does exploration in an uninformed way. At each time, there are a set of nodes that are open. This is a priority queue. So each node has a priority. And you keep track of the cost to come, CTC. And every time you try to you spend the one which is the lowest cost to come. So this is not very efficient because it spends basically, it doesn't know where the goal is. So it spends from the goal in all directions. There's an algorithm called A star, which is a slight variation where you have additional information. A star does what is called informal exploration, and there's a heuristic function. The heuristic function is actually a lower bound on the cost to go from a node to the target. So now in the priority queue, you have for each node also not only the cost to come, but also the cost to go. And now the priority is the sum of these two costs. So this is a very small modification of the algorithm, but now, as you can see, once you get over this area, the algorithm will be able to just go down, minimizing the cost to come plus the heuristic. Right? So this is the simplest algorithm that is not topless. All right, so now let me generalize this. So in general, we call an algorithm, such algorithm complete if we can find a path, if the path exists, or give a certificate of infeasibility if one doesn't exist. So the path here is positive information, and that's a morphism. A certificate of infeasibility is unclear what it is, but it's negative information. Now, an optimal algorithm can find an optimal solution. So what is an optimal solution? Is a feasible path together with a certificate of optimality, which typically says that there is no path which is better than this. So again, this is positive information and there is negative information. Then I showed you A star. So A star also has heuristics, which are lower bounds for the cost between 2 points. So this is negative information. And what I'm going to show you is that this formalization can capture all this negative information using what we call norphism. Now, more in general, when you do applications, it is very typical that you have some kind of inference algorithm that is running and that produces feasible points as morphism. So imagine you have your category, you have your objects X, Y, Z, and these boxes represent the hom-sets. And at each time, you have some morphism that you call proved, which means that they're valid in your context, okay? Some that you have disproved, and some that you don't know. And now let's assume that everything is decidable. So there's no like something that you cannot know. Now, if you have an algorithm that just reasons on, run some kind of algorithm and just improves these estimates and just expands the elements that you know, but doesn't have any way to actually disprove anything. So you're in this situation where you might have absence of evidence, right? So you have something that proved, but you don't know whether the others are provable or not. As opposed to having evidence of absence, which means that you actually have something that's proved that you know they're valid and something that are not valid. So in general, this work brings up the negative part of category theory, right? So where there's going to be some part, the morphisms that are the positive information, and norphism will be the negative information. I staggered a bit during this slide because I saw there's Dana Scott on the call, so I was trying to think, what assumptions I need to put on this iteration for it to converge or whatever. But yeah, I think I came back to myself. All right, so let's do the case of thin categories. By this I mean a category which is just one morphism per hom-set, And basically, these are pre-orders that we can take to represent connectivity. So it's just like with the motion planning without costs. And I will give you some postulates here, and we'll see the consequences. But then I'll give you the general formalization by induction. I'm going to call N a norphism, and I'm going to write it as this dashed arrow. And I'll give you the postulate that if I have this norphism from X to Y, that implies that there is no morphism from X to Y, and vice versa. So a morphism from X to Y implies that there is no norphism from X to Y. So what's interesting is that if you think in these terms, you find that these norphisms seem to behave with the dual rules according to the morphism, right? So now dual means that you put them upside down and you negate them, right? So top at the top becomes false here, and morphism becomes norphism. So I read it. So it's always true that there is a morphism from X to X, and but it's always false. It cannot be that there is a norphism from X to X. Why? Because there's already a morphism from X to X. If I try to turn this around, I get the following, right? So this is an end, right? If I have an F and a G, means I have an end, right? Then I have this composition. The opposite would be to say that if I know that there is no morphism from X to Z, then for every object Y, I know that either I cannot go from X to Y or I cannot go from Y to Z. Okay. Otherwise, this path would be possible. Now, this is also a very non-constructive way to put it, right? Because we have an OR in the conclusion, so we don't like that. So I will write it again in a constructive way. So let's look at this diagram. So suppose that you have a morphism from X to Y, F, and a norphism from X to Z. Now, apologies for the red here. There should be black. The object should be black. So what you can infer from this is that there is a norphism from Y to Z. Why? Well, because if there was a morphism here, then you would have a morphism from here to here, which would negate this norphism. So this is now this is one way to compose this norphism, and then there's the symmetric way. So in this case, the norphism and the morphism come from the same source. Here they have the same target. So it's actually two different signatures, and we use these two different symbols. The mnemonics here is that these two little dots means that they go to different targets, and this one means they go to the same target. What we notice here is that you always need a morphism as a catalyst, and you cannot have a norphism plus norphism composition rule, because the fact that you cannot go from X to Y and you cannot go from Y to Z doesn't imply that you cannot go from X to Z, right? Because there could be another route. So what we find is that there is no category of norphism. Norphisms are complementary to morphism, but have different rules. This is the definition that I put forward of nategories. And so this is a locally small nategory. It's a locally small category with some additional data. Right? So for each pair of objects, X and Y, in addition to the hom-set, we also need to specify a nom-set, a set of norphisms. And we need an incompatibility relation from norphism to morphism, which we write as a binary function. Now, for all triples, X, Y, Z, in addition to the morphism composition function, we require that there are also these norphism composition functions. And each of those takes a morphism and a norphism and gives you a norphism. Then I will introduce these equivalence conditions. So this will become more clear in the future, in a few slides. But I just want to say that what we want from this norphism composition operation is that they only look at the categorical structure, right? So they don't use any additional information that you might have. So if you're creating the norphism Fn and you exclude a morphism G, the only reason you can exclude it is that because the composition F and G will be excluded by N. I will show you some examples of this in a few slides. The last definition, if these conditions are satisfied with the in the other direction as well, we call the nategory exact. If you give me a category, I can construct a nategory in a few canonical ways. There's a construction in which you just set the norphism to be the empty set, and then you have to define this function I and this composition operations, but their domain is empty, so that's it. And that's a valid nategory. Another construction is where you say, let me just put one norphism, which is this red dot, and you set for the incompatibility, you say, well, I want this to be compatible with the identity, so it's not incompatible with identity, but for it will be incompatible for every other norphism. And then if you set this to be the codomain, then these functions are fixed. And this is also a valid nategory. So what this does is this is basically negates you have very rough information. You can just say that I will exclude all the morphisms except the identity. Now, actually, if you have actually, I'm a big fan of semi-categories in general. So actually, if you're working with semi-categories, then you would be fine in excluding also the identity. So you wouldn't have this case analysis. Or you could have another semantics where if you exclude the identity, just like you're excluding the entire object from validity. Right, so these two are the really trivial ones. Then there is the maximum formalization in which you set the norphism to be the power set of the morphism. So now you can choose exactly which morphisms to exclude. Now, if N is a set now, so the incompatibility condition is that it's incompatible if F is contained in N. And you can derive now these operations as using the precomposition by F, the inverse of precomposition and the inverse of postcomposition. I will show you later like a diagram for this. The definition of category is very broad. There aren't many conditions because I'm also happy with allowing very weak inference rules. So for example, you could have sets like before, but then you can just say, every time I compose the norphism, I get the empty set. So this is not very useful, but it's still a valid category. Now, I'll give you the intuition of this, what's the logic behind this formalization? Well, this set-based, power set-based formalization. So let's start from here. So suppose that you have a norphism N and a norphism F, morphism F. So N goes from X to Z, F goes from X to Y. The operation gives you a norphism in Y to Z. So the way you do it, you start from N, and you compute the set of all incompatible morphisms with this operation. So J, X, Y, from a norphism, you get all the morphisms that are incompatible. Once you do this, then you can pull back the using the precomposition with F, and you obtain another set here. And then you say that, well, my norphism, my N composed with F is going to be this set. And this set will be exactly that set. In the case you have, you can express all possible subsets, otherwise it will be something included in it. I'll give you another example about hiking on the Swiss mountains. I'll define a category Berg. Berg means mountain in German. And this is just a manifold. So the objects are elements of the tangent bundle, and paths are the connection between those points. And then we are going to, for fun, we are going to also define the steepness of the path at each point. And then we're going to define some bounds for the steepness. And so we're going to say, well, the morphism that we take as morphism only the paths that are not too steep for us. Here's a possible formalization. So I can take the norphism for Berg to be the lower bounds on the path distance. So I'll take the norphism to be non-negative integers, and I can also add plus infinity. I can complete with plus infinity. That means that that will be a negation of the possibility of any path. And the incompatibility condition is the following: n is incompatible with f if the length of f is less than n. And the idea is that n is a lower bound, so f shouldn't violate this lower bound. Now, finally, we can say what is an optimal path with our formalization. Well, an optimal path is a feasible path together with a lower bound on a distance, which is a norphism. So an optimal path is an f from x to y and a norphism from x to y equal to the length. These are the norphism composition rules. I'll do the same logic as before with connectivity, just with distances now. So suppose that you know that going from x to z will take at least n, and you know that you have f from x to y. Then you can say that going from y to z takes at least n minus the length of f. Otherwise, you violate the assumption. Now, I defined that rich category because I want to give you a few examples of norphism schemas. How do we generate the norphism in the first place? First of all, because any path has length at least 0, then 0 is always a valid norphism. If you take the points, if you take the distance between points as the distance in 3D, then moving on a manifold will not be faster than going straight. So the norm between P1 and P2 is a norphism to go from this tangent point to this tangent point. Then, because you have a manifold, you know also that the geodesic distance is a norphism. And the reason I add that those steepness constraints, so where we constrain to be from the path not to be less steepness less than sigma u, is that now if we need to climb, well, we know we need to climb a distance which is bounded by something over the inverse over sigma u. So there's something to do here for future work. Now you can see you can rank these axioms, right? Because this is the weakest one, right? This is stronger. This is even stronger, and these two actually are not comparable with the others. So a theory of subnategories would be one where you actually classify the norphism axiom, the norphism schemas. So just to finish this example, let's verify these conditions, right? This is the condition that needs to be verified for this to be a nategory. And then there's this exactness condition where you want or the other direction as well. So it turns out that if you, with this choice, which is very intuitive, where you have non-negative numbers as the norphism, it's a valid nategory, but it's not exact. And actually, the exact version is where you let the norphism to also be negative numbers. And the composition simplifies, and it's also exact. So somehow you can carry like bounds with negative length are more informative. You can carry that information through. In general, you can use approximations, but they need to be conservative. So for example, if you can use the integers instead of the real numbers, but you need to use a floor instead of round, because floor would tend to exclude a subset of the possible morphism, but it's included in the morphism. It's included in the real subset. Instead, if you use round, if you round up, you're excluding more norphism that you're allowed to. Okay, so I will now go to the next part. And the next part is about using a rich category theory to recover this structure. This is the definition we're going to use. I will just read it for the notation. If you have a modular category V, a V enriched category E is given by a tuple of E, alpha E, beta E, gamma E. So of E are the objects, alpha of X and Y gives you an object of V, and beta is the one that gives given triple gives a morphism of V. And finally, gamma is the one that goes from the unit to alpha of X of X. This is so this is the basic example of enrichment. Sorry, I forgot to write what is P, except on the first page. Yeah? So P is set with the Cartesian product as a modular product. So if you have category enriched in that, then you have the data necessary to define a small category, and vice versa. I'll do this because then I will do the generalized version. So suppose that you're given a P-rich category, so you have this tuple. What you do, you set the objects of C as the set of objects that you have. For each X and Y, the function alpha XY gives you the hom-set. And for each triple of objects, you get this function here with this signature. So XY with Z, XZ. Now, the diagram constraints that this imply that this function is associative, so you can use it to define morphism composition. Then, by using the last data that you have, this gamma, you obtain a function from 1 to the hom-set of XX that selects a morphism. Now, that morphism happens to satisfy unitality with respect to this composition because of the diagram constraints, and so you define that to be the object. Now, I will build towards a category that we call PIAN, which is based on the GC construction by the PIAN, which is an incredibly rich construction. I met it the first time when I was trying to get into linear logic. And what's really interesting is that it provides a non-trivial model of linear logic, where you have 4 connectives, 4 units, the negation, and 2 modalities that are distinct. There is a recent blog post by Nelson on the website that clarifies the relation between GC and poly, but of course going to another level of generalization. So now we will do something much more simple. So this is the plan. We actually just use the G set. We will see some of the monadal products that are defined by the PIAN. We see actually we need a slightly different one to add to the collection. And then that will be the one that we use as target for enrichment. So we will call PN the monadal category G set with this new monadal product. This is the basic definition of G set. Each object is a tuple where you have a set, and the relation between the 2 sets. So a morphism between 2 objects is a tuple of two arrows. So there's the backward and the forward. So flat would be down and looks like a B, so that's backward. And sharp will be up to mean forward. So the backwards goes from Q2 to Q1. Instead, the forward goes from A1 to A2. And this is the property that needs to satisfy. So for all Q2s and A1s, you have this condition here. Now, before I read the condition, I'll give you the interpretation. I use different letters than the original paper because I like the questions and answers interpretation, where you say Q is a set of questions, A is a set of answers, and C is a correctness relation. So if you have QCA, it means that A is a good answer for Q. With this interpretation, then morphism become reductions of problems. So in particular, a morphism from Q1, A1, C1 to Q2, A2, C2 is a reduction of the second problem to the first. So let's read it. So suppose that you have a question of the second problem, Q2. You can apply the backward part to obtain a question in Q1. So now, assuming that you have an algorithm to solve the first problem, you get an element of A1, which is the answer to the question in the first problem. And then you can push it forward to get an answer to the original problem. The morphism, the condition that is satisfied basically allow you to do the trick. So the independent variables here are Q2 and A1. So this says, again, if I have a question of the second problem and I transform it in a question of the first problem, and I find an answer that's correct, then if I find the corresponding answer of the second problem, it will be correct for Q2. All right. Now, I give you the same formalization a little bit more general, where instead of having a relation, so a function to bool, you have a function to object of any category. So let be a category with finite products and coproducts. And actually, you can think of B as bool, at least for now. We slightly changed the definition. So we now have a tuple of Q, A, and kappa is a function that goes from Q times A to the objects of B. A morphism now has three components. You have the backward and the forward functions. And then you have a dependent function that for each Q2 and A1 gives you a morphism of B. Now, I don't need any, I just need sets. I just want to say that if this was cat, then this would look a little bit cleaner, because this would be, kappa would be a profunctor, so of which you just see the object part of the functor. And this thing that takes two objects, an object into a morphism, the thing would be a natural transformation. But the reason I do this is actually because I'm taking the homotopy type theory class, the hottest class, and it's very fun. So now I prefer to do morphism composition rather than logic. And this is the reason. So if you have these two, we have this definition of morphism, then I can say that the composition of R with S is, again, forward composition, backward composition, and forward composition. And then I can just use R star and S star to obtain this morphism. Yeah, which type checks, so this is correct. So I don't have to do any logic. All right. So I will now show you a few monadal products. GC is very rich. I like to be very explicit with the notation. So when I define the object part of the functor, I will put a little dot. When I define the morphism part, I put a little r. So this is the first monadal product. It's very intuitive. It's the first thing that comes to mind, right? So I want a product. I will just take the product of the questions, the product of the answers, and the end of the predicates, which would be the end in bool, which is the product in bool, and general the product in B. The unit is 1, 1, true. So 1B is the terminal object in B, which for bool is true. And then you take if you want to get the product of the morphism of R and S, you obtain this. Very simple. So you you take the product of the functions, and again the product of the morphisms. So unfortunately, this is not so this is not the product that actually gives the nice interpretation of GC in linear logic. For that, you need to define this tensor product. And this is a little bit tricky. So this is the only tricky thing that there is in the entire talk. So if you have a Q1, I1, K, kappa 1, K2, I2, kappa 2, I take the product of the forward part, as the Cartesian product. But for the questions part, instead of taking Q1 and Q2, I'll make them dependent on the answers. So this notation means it's a map from A2 to Q1 and a map from A1 to Q2. So this is a game now in which the questions depend on the answer on the other channel. So the unit is the same, is true. And this is the product. So for the forward part remains easy. It's always trivial, right? So just like the product of the forward part. For the backward part, well, now you have to provide two functions, and you obtain these two functions by precomposing and postcomposing with the forward and backward parts, but they're mixed. So this we have S sharp something R backward. And this is the product, which for the last part, this is the proof that the morphic condition is satisfied. We just agreed it's the right type, so it's the right one. The other one is the dual. So this is these two monadal product makes it a sigma, a star autonomous category with the negation that switches the position of questions and answers. So now this par is usually called in linear logic. Now you take the product of the questions and you take the product of the answers, but made into an independent function. And you use now as the unit 1, 1 false. The definition of the product here for the morphism is similar. You just switch things around, and now you have a coproduct instead of a product here. So we needed one of these monadal products. Actually, neither of those works. So we needed to define a slightly different one, which is the following. So basically, this takes the times monadal product signature for the objects for the first part. So it's a product of the questions in independent form, product of the answers. But here we actually use the coproduct instead of the product. So it's an or instead of a and. And the unit is now 1, 1 false. So this is a mix between tensor and par. Okay, so now I'm ready to study my result. I'm just going to define the category PIAN to be the monadal category. So with G, set, and bool to B, and with that new monadal product. And then this is the main statement. If you have a PIAN enriched category, you obtain the data to specify nategory. However, actually, it turns out that this nategory that you generate is actually much stronger than the set of all nategories, because you actually have these additional properties, which are things that you might want to require or not. But you know, I prefer to have a very weak definition of nategory. So you obtain these neutrality conditions. So the two composition operation have an identity. The identity is the identity. You have these distributivity conditions. I don't know how to call that's a distributivity. So if you have F, then G composed with N, it's just like N composed with F and then composed with G. And at this point, I realized that we had to switch the order because you see we have FG instead you have GF. But yeah, you never know at the beginning. and the other is similar. So N composed with this other operation, G, then H, can expand in this. Plus, there's a mix of associativity conditions with these the two operators. So F composed with N composed with H is just like F composed with N composed with H. I will give you a short, the interesting parts of the proof. And this is now a generalization of the proof that I gave you before, of the fourth lemma. It goes like this. So suppose you have an enrichment in PIAN, which means you have this function alpha. Evaluated that two objects, it's two sets and a Boolean function. And we take that to define the norphism, the morphism, and the compatibility relation. Then for each object, you have gamma, which is a morphism from 1 to alpha of xx in PN. So you expand this, you turn this morphism R from false to this. Now the forward part is the one that picks a morphism from 1 in norm xx. The backwards part actually are not informative in this case. They just give you backwards condition. Now the composition operations, that are interesting ones. Now for each triple x, y, z, you have this object, you have this morphism beta x, y, z, which is from the product of two objects to another one. Now I just expand this in our case. So each object for us now is a norphism, morphism, and incompatibility. And then I expand the definition of this tensor and obtain this morphism. Now, so what I learned is that it's easy, just go component by component, because the components are in parallel. So there is a forward map that goes from hxy to xyz to xhxz, and that's just morphism composition as before. But now the backwards part actually gives you something else. So there's a map from here to here, so from here to here. So this is a map from a norphism to a pair of functions that depend on a morphism. So I can rewrite this as two maps that happen to have the right signature for our norphism composition operations. Now the last component actually gives me the proof, and so this is because now I have a three-line proof. It was worth to have this weird morphism definition of GC. So this I just expand the definition. So I evaluate S star at n f at g, and expand. I get this. I get a morphism from the coproduct of this object of Boole to this object of Boole, and this object of Boole to another object of Boole, which is a pair of morphism from this object to this object, and this object to this object. So I obtain this morphism of Boole. So what I obtain is exactly the, now I go back to the interpretation and logic, that's just an implication. So this defines a valid nategory. Now, what it also defines as a side product are these additional properties that derive from looking at the constraint, the diagram constraints for enrichment, which are not necessarily satisfied by all nategories. So in some sense, we found a category a little bit too strong to reach on. Now, I'll give you another example. So this is actually the category that David was talking in introduction. He likes to call it Boolean profunctors. I like to call it DP for design problems. Now, design problem is a tuple of two posets and a monotone map, which is a profunctor. And composition, if you have two of them, you can put them in series. And it turns out that you just take the or over the common element. Now, I think that there's a slide missing here. So let me just go back to the definition one more time. So I just wanted to sorry, 1 second. Right. So far we've been talking about regular categories where there's not a structure on the hom-set. So the hom-set is just a set, and so we said the norphism is just a set. But there are categories that are more structured. So, for example, they're locally posetal. So you would have a poset, and then it would make sense to have another poset of norphism. So you could do the same thing by just enriching in G pos instead of G set. Also, instead of bool, you could have let's say set, for example, in which you would actually have some notion of proof relevance, a little bit of explanation. So you just, in addition to say whether a norphism and a morphism are incompatible, you also need to give me the reasons. Now, let me go back. All right, so I think we are the last slide here. So conclusions. So actually, this theory of that allows you to categorify negative information with these new arrows that we call norphism. So what's to take away here is that norphism and not morphism in a different category. They compose in a different way, and they compose using morphism as a catalyst. Now we defined nategories to be categories that also have some accounting part for this norphism. And what we showed is that these rules, which seem a bit arbitrary, actually can be derived from rich category theory. So just like a certain rich category theory, certain rich category gives a small category, a PIAN rich category gives you a nategory. Where PIAN, I remind you, is an extension of the GC construction by the PIAN. So Fisher work, this current enrichment actually is a bit too strong, and this is more probability that we want. So we are still, this is still a work in progress. We're in the process of surveying what the natural norphism structure is in the wild with the commonly used categories. And especially for applications, it's actually very fun to look at the algorithms and see actually pinpoint where they're using positive and negative information. As Fisher work, there's also the generalization to higher level concepts. What would an anctor be? An anctor would be something that is a functor, but also does something to the norphism. And we don't know at this point what is a good generalization. All right, thank you for your attention. This is all I have. I'm happy to take any questions.
Thanks, Andrea. Okay, so are there questions? We've got a lot of claps in the chat, but if you have a question, either raise your hand in the chat. Oh, Valeria has a question, please. Valeria.
Hi, Andrea. That's nice. Can you hear me properly?
Yes, I can.
Cool. I have two questions actually. One of them is the business of I have done a version of GC that is over posets too. So kind of there is another preliminary work on that. But
the one with multi-relations.
Using relations, but doing the category C being posets. So, you end up having a notion of different proofs or different problems, as you want to say. That's cool. And I also done kind of quite a bit of work on problems and solutions, because this is actually a very old idea of Kolmogorov. Andrei Kolmogorov came up with this notion of problems and solutions. And in 1932, believe it or not. So there's another paper along these lines. But the question that I have is this business of the new monoidal category that you came up with, which uses that in the carriers, it uses the conjunction, but in the predicates, it uses the disjunction. So I was kind of wanting to know, why do you need the disjunction in the predicates? Can you give me?
Yeah, so we spent the last 2 weeks thinking about this. So one thing that I wanted to take GC without changing the direction of the arrows. So I want to just take natural GC. But then it actually turns out that I need this. First of all, it's very similar, so it's just changing that. It turns out that I really need this coproduct because in the end, that coproduct will show up here, and there is this nice trick that I get this morphism from a coproduct, and then I can split it into. So now I have two of the morphisms, from this to this and from this to this. And because I need these two, because actually I need these two different conditions. So this is actually what we did, to be honest. We wanted to get here, and we worked back to see what was the monadal product that we needed. So it's a completely technical reason, and it's and that's. I wish I could have used the other ones. So I don't exclude that. I mean, sure, of course, if it's you, maybe you can find a way to do some wrangling. But we were not. This is the best we could come up with.
No, that's very interesting. I like it lots. Yeah, thanks very much.
I want also to tell you, so actually the paper that I really like, the paper by Blast, Questions and Answers, actually the one that actually made me very, very intuitive for me. What is interesting here is that, so in that formalization, you have questions and answers.
Yeah.
But now you actually have negative information. So it's like this counter examples and proofs. So that's I think that's really interesting. I didn't do it, but kind of see whether these semantics actually, in the style of the Blast paper, right, where you now look at all the monadal products and you see what's interpretation and linear logic. I think there is something interesting there.
Yeah, I think it is true that from the beginning the idea is actually Gödel's, that you should have proofs and instead of counter proofs, counter examples. And
guys, can I interrupt? I'm sorry. I just want to get as many questions in, but thank you, Valeria. That was a great question. David Yetter was next.
Not so much a question as a comment. One of the extra conditions you got that you didn't particularly want when you constructed your nategories as PIAN enriched things are ones that I would have actually expected from the very beginning. I mean, there's a moment I saw your actions of I saw, the morphisms act on the norphisms, and I would have thought that an action should satisfy exactly those three conditions that you got there. If you think of the category as sort of a many objects analog of a group or a monad, and then you've got a way of making things going the opposite directions from the morphisms into the obvious notion of module over it. You would get exactly those the conditions you've got there. Okay, so I'll give you my reasoning. So first of all, this is a matter of definition, so it's a bit matter of style. But if I think in terms of purpose, I really think about these operations as some kind of inference operation, where this inference can be exact or can be very weak.
So actually, if I go, so this is the exact version where it is the best morphism structure where you have all the subsets, and now this is exact in the sense that you get all those properties, because yes, essentially you're just moving, translating things around, right? But for applications, I really like to include the very stupid inference things like this, where you just say, I don't know, I'll just give you the empty set, a very, very weak inference rule. I'll give you an example. I think a good example, now I understand that, the first time discussing this is a bit, I don't know if all the examples came up, were clear, but for me, so we showed here that if you take, this is for you have this kind of metric space, and you have lower bounds, and then this is the right way to do it. And then I like that there is a version where, well, maybe I don't have all real numbers, I only have integers, and I can still do something, and that something will be valid, and then I can go on with my life, right? So I think really the algorithmic purpose has influenced the choice here. But yeah, so actually, so now just for the others, because it was clear to you. So here, basically the identities that we get at the end from this here, what we get, usually we get that in only one direction, in the sense that the morphisms that are excluded from this imply that they're also excluded from this, but not vice versa. So from these actions, you can get something weaker here. This is very strong. So these ones are actually super strong, extremely strong. This one actually seems natural, but still.
That's the analog of being a bimodule. The actions on the two sides commute with each other.
That's right. That's right. I confess I never took a group theory class. That's right. I didn't see it. Yeah. That's right.
Okay. Well, thank you for the question. I think let's move on to Patrick Campbell as a question.
I was just kind of curious, so does this, so say you have a robot in a space and like something that seemed infeasible is now feasible, and so you have some update, and is that kind of where nunctors, is this the matter of nunctors potentially, or?
I don't think that's a matter of nunctors.
Okay.
But it's a beautiful question, because so usually, so the usual setting is where you have more information, and then more information is the refinement of the information that you had before, rather than negating some information that you had before. Right, so it's you will have think of these things like in a Scott domain, right? So we know you have some operation that gives additional information. So you go up in information, and then you go up in the conclusions. And usually, but if you start to remove some information, it's really a mess. And actually, it happens in robotics a lot. And that's the case where you would have you're either finding a solution. The solution is optimal, assuming that there are no other paths, because of all the data that you have, right? But if now, for example, there's a link from T to M, then you need to invalidate a lot of the structure. So it's not monotone anymore. And there's actually a family of algorithms that can do this by let's say, repairing the graph. Well, there are two cases. Either there's a new, actually, sorry. So there are two cases. Either there's a new connection. Actually, that's fine. But if a connection that is removed, then you really need to do something complicated to the graph to recover. For the nunctor, I'm actually, please let me know if you find a good interpretation, because it's not clear. It's really not clear to me at this point.
Great. And I think we have time for one last question from Nelson.
Hi. Hopefully you don't mind. There are two quick questions I want to ask. First of all, let's see. So I remember during your ACT talk, you had a different characterization of PN. So is the data, like now that you've defined it in terms of the GC, is the data of that category different now? Is that like, or is it like roughly the same? Is it, and does it make enriching over one versus the other, like change those extra conditions that you have on that?
So I will, being honest, like we did a lot more work with this formalization than the other one, because we were much more careful about looking at all the diagrams and what conditions they derive.
Right.
I think that but basically I think it's the same, but written. But so now, I guess you remember there was like this dependent function things. So
Right.
basically what happened is that, so here's the thing, like we had this function to be dependent, like the backward function, which, nobody's scared of that, right? But then it's, we found that actually if we use a GC construction, we could let that be just a regular map. But of course, the dependence comes up somewhere else. So you actually get the dependent function here.
Right. Exactly.
But this is supposed to be in the general case a natural transformation. So that is nice. So that's where you would expect it to.
Right.
So in general, I think we went towards simplified overall in terms of a kind of cognitive load. But mostly they've been, let's put it like this, they've been reverse engineered for the same goal.
Right. Okay. My other question was this like nunctor business, right? So there is the natural sort of like definition of what a functor is, right? Like between what an enriched functor is, right? So is that definition, right, like not somehow like the semantics like don't seem to work out, or what are you looking for in a nunctor, I guess, like, and even like some thoughts on that, I guess.
Yeah, so actually, I have there's two directions here.
Right.
One is to say there's something called a functor that acts on the morphism, but also on the norphism. So that's one way. Another one is actually to say, no, there's a functor and then there's a nunctor. So I don't really know, but it's really tricky because, well, I guess you have in mind, I want to show you that, the usual functor diagram, like X, Y, Z to X, F, right? That's all very natural. But for example, these norphisms are not really arrows. And not really arrows in the sense that you have diagrams of them, because you cannot make diagrams. There's no composition in this direction, right? Right. So there's no, I don't see like maybe you see it and you let me know, but I really didn't see like the one that pops out as the graph. What's the diagram? And then it pops out. That's an obvious definition, because you cannot do the diagram for the norphism. Now I don't. So but that there's so many. I think maybe a different graphical notation. There's all kinds of string diagrams, with the areas like this, so that this is not these are not arrows, these are like cells or something like that. So maybe that would provide the intuition. But really at this point, I don't know. But usually what would the obvious thing would be something that if I had two problems and the functor is kind of a translation between the two, then a nunctor would also tell me that some counterexample of one, counterexample of the other one. So that would be the interpretation.
Okay, cool. Thank you so much. Yeah.
Okay, well, let's thank Andrea again. Thanks. And I'll stop the recording, and maybe some people, I don't know if you have time for like another question or something.
Oh, sure. I can stick around.